Now that we've identified turbulence as a condition that occurs when inertia becomes sufficiently large relative to the stabilizing viscosity effects, we can look at when that occurs in other types of flows. So we know that for pipes and ducts, that is flows that are contained in some kind of a container, we call those internal flows. We'll be looking at that again in a minute. But those internal flows, or the flows internal to some pipe or a duct, we found that there's a transition criteria that we can use, that is the Reynolds number based on D is about 2,000. So that's the transition moment for turbulence in those types of flows. A more generally useful transition criteria, which can be applied, if applied correctly, to a lot of different flows, and is sort of a good initial guess. If you're not sure whether it's gonna be turbulent or not, or whether it might be turbulent, a good transition guess is that the Reynolds number will be 100 when it transitions to turbulence, based on L, this little L here, not the length of a pipe, not the length of a plate. This is the size of the obstruction. So what L is depends on what the flow is that we're talking about. We'll give some examples in a minute. But basically, this is the size of the flow deflection, the size that the flow is being forced to go around. This is most generally useful for what we call external flows, where the flow is flowing around or over something rather than where it's flowing inside something. And we'll see that because when the flow is inside a pipe or a duct, that stabilizes the flow to some degree. That inhibits turbulence because it's in a confined space, whereas these flows transition much earlier because they are, free to spin and swirl out of control, sort of in open air. So a classic example of one where you see this would be flow up some kind of a step. So you have some kind of uniform flow coming in here with some velocity, u infinity, and there's some step. Maybe I'll call that step H in this case. And so the flow is going to, initially, if it's very slow flow, it will just come and gently go over the step as we've been drawing it for laminar situations. But if that Reynolds number gets of order about 100, so in this case it would be Reynolds number based on this H height, because that's the size of the obstruction, when that gets to be about 100, you're going to start to see turbulence. Where is turbulence going to actually occur? Turbulence is going to occur after the step. So it's going to hit the step and it's going to deflect up, and then it's going to swirl and roll into turbulence. So this is called this is a turbulent, essentially wake regime. And this is typically what we're going to see with these external flows. The turbulence will occur after the obstruction in some form. And so that's your criteria, roughly, for turbulence in that type of flow. Another flow that's an obstruction type flow is flow around a cylinder. So here we have a cylinder with its typical diameter D, and the flow is coming in from the side again. Of course, the side of a cylinder is any direction you want, since all sides are equal, it's circular. But anyway, flow coming along, and this is your D, and if the flow is laminar, the flow will do this. It will smoothly go around the cylinder and come out the other side, like that. That would be laminar. But if it gets above Reynolds number based on D of about 100, you're going to see turbulence in the wake region again. So again, in this case, I'll draw a new picture. You've got this cylinder sitting here. The Reynolds number goes above 100 based on D, the diameter, the size of the flow obstruction. And so you have, it goes up like this, but then in the wake region, you get turbulence. So it goes around here, and then it starts to do this. And so you might have some kind of turbulent wake in the back side of the cylinder. So that's how that looks, and that's how that will happen if the Reynolds number gets above about 100. Another flow that has a similar transition criteria is a backward facing step. So in this case, we can call this H again. Flow coming this way. You can imagine that this wouldn't be turbulent, but it is. So again, slow flow would just kind of do some kind of smooth transition down the step. But in a turbulent situation, this would cause some kind of turbulent swirl in this region. So it's going to be a turbulent wake after the step if, again, the Reynolds number, H, gets to be about 100. Final one we'll look at for this type of flow is jet flow. So jet flow, you have an isolated jet of fluid. We've been looking at a lot of jets recently, so we have some jet of fluid here moving in this direction. And we saw this in class. Well, you sort of saw it. I wish you'd seen it better. But we saw this in class with an upward jet when we had the candle. We have a laminar region But at some point, if the flow is getting faster and faster, that jet becomes turbulent, and the criteria for this will make the jet diameter once again be d here. If the Reynolds number based on d gets to be about 100, then you see a turbulent jet. And the turbulent jet, of course, will do what we saw. It will start to spin and swirl out of control and expand like this. So that is a good guess. It's not that this is precise. I put approximate signs on all of these. People have been doing lots of experiments on when these actually transition. Some people say the jet condition is actually like 30 or 35. As we saw in class, it depends very much on the ambient conditions around. Like if you disturb the jet at all, it will go turbulent earlier. If you blow on it, move near it, put something in the edge of it, all those things will trigger or trip turbulence. Similar to these things, if there's some kind of little bump here or little bumps, that will tend to trigger turbulence earlier. If you have smoother situations, turbulence will happen later. But roughly, knowing that turbulence in many, many flows will happen at a Reynolds number of about 100 if you're talking about a flow obstruction. In this case, a jet, it's not really a flow obstruction. It's just when it gets, to that size of 100, it just becomes unstable. So a little hard to think of that as an obstruction, but it is nonetheless about the same Reynolds number that you see for that jet becoming turbulent. So the final thing I'll point out is it's very different from the Reynolds number you see for flow over a plate. So for flow over a plate, if you want to look at the turbulence transition, so here's flow over a plate. The number you'll see for this transition is about that it transitions at Rex is about equal to 5 times 10 to the 5th. Hugely, hugely different from 100. So here's the laminar regime here, the delta, the laminar boundary layer growing, and then it tips into turbulence. I'll show you in the next lecture that actually this can be understood to be much more in keeping with this if you look at this differently. But nonetheless, this is a number you'll see a lot. Transition for flow over a plate is around 5 times 10 to the 5th. And again, these numbers are not firm. Certain situations will have turbulence earlier. Certain situations will have turbulence occur later. People don't even really necessarily agree on these numbers. But these are still nonetheless the standard numbers that you can keep in your head. So if you just want to even consider, could it be turbulent or could it not be turbulent? This is a good number. If it's 1,000, it's going to be turbulent. If it's 1, it's not going to be turbulent. That kind of thing.